Hey, Chem30, welcome to topic 6 of unit number 5. This is neutralization. So a neutralization is a specific type of double displacement reaction. So we saw double displacement reactions in unit 4, the solution equilibrium. Sometimes those are called metathesis reactions, but these neutralization reactions are when we take an acid and neutralize it with a base or vice versa, which always produces the same two products, water and a salt. The salt is different depending on the type of acid and base we're using, but it's an ionic compound dissolved in water, and that's what we're going to consider to be the salt. Okay. So acidic solutions are those that contain the hydrogen ion and have a pH of lower than 7. Basic solutions are those that have the hydroxide ion and have a pH of greater than 7. When acidic and basic solutions are combined or neutralized, a new pH is reached because the H plus reacts with the OH minus to cancel out and produce water, which is neutral. Okay, so the equivalence point is reached when the concentration of hydrogen ions is equal to the hydroxide ions. Okay, so it moves, basically we can imagine having an acidic solution. Okay, so this is acidic, and then we slowly add a base to it until we get to the equivalence point, EQ point. Okay, at that equivalence point, the concentration of the hydrogen ions and the hydroxide ions are equal, and that's really important. So the reason why we do this procedure or neutralize something through a process called a titration is because strong acids are made by bubbling gas into water. Over time, those gas molecules come out of the water and the concentration changes, but we don't know by how much. So for example, when we order hydrochloric acid, concentrated or stock solutions is what they're called, it has a molarity of around 12.1 molar, so very high, very concentrated. Over time, as it sits in our chemical storage room, that hydrochloric or those hydrogen chloride ions come out of solution, so the concentration changes, so we don't know what it is. So, and that becomes really important because if we're going to do an experiment with it, we want to make sure that we understand or know the concentration of the chemicals we're using because it'll affect our results. So in order to do that, what we can do is we can create a base which we know the concentration of. So let's just imagine here's our acidic solution, and we know the pH is low. We'll just say low here, but we don't know how much is there. So we're just going to write a couple of question marks. Well, if we can take a base and neutralize it and see the point at which the equivalent or the pH hits 7. So let's say that we've got a pH of 2 and we add a little bit of base and the pH changes to 3 and then it changes to 4 and then it changes to 5, right? So we can keep on adding base, canceling out those high or H plus ions, and eventually it's going to get to a neutral solution where the pH would be 7. And what we generally use is something called an indicator. An indicator will tell us what level of acidity or what pH a solution has. Think way back to the very first topic where we had those indicator strips or universal indicators. We have more specific ones. We have better quality ones than litmus paper or universal indicators that we use for titrations, but it marks the point at which a solution moves from acidic to basic or from basic to acidic. And we can see that point, and we'll see how that works in a calculation. Okay, this procedure together of figuring out an unknown concentration of something is called a titration. Now there's this video here. I'm going to put this video in our online video portion. You only have to watch the first 3 minutes and 10 seconds of that. Okay, but I'm going to stop right here. Watch those. It gives a pretty good walkthrough of what a titration is and how that procedure is going to be used. So in a titration, we should recognize that the concentration or the number of moles of H plus is equal to the moles of OH minus. So for example, in that video, we're just going to play on that a little bit more. So if we take a concentration, right, in moles per liter and multiply it by a volume in liters. So in that video, it said 48.6 milliliters, but that would be 0.0486 liters. What's going to happen to the liters? Well, they're going to disappear and we're going to get number of moles. So if we have a concentration, a known concentration of our base and a volume of that base, which we use the burette that standard solution is in, we can figure out how many moles of acid were there. So For example, if 0.2 moles of sodium hydroxide was used to titrate a strong acid, it must mean that there's 0.2 moles of H plus present. If we know the volume of the acid in the sample, right in the video it said 20 milliliters, and we know the number of moles of H plus, we can figure out the concentration of the acid. So these are the steps to solving a neutralization equation. We're going to write and balance an equation. We're going to figure out our unknown and known variables. We're going to determine the relationship between the moles of acid to the moles of base. So in that, think NaOH and H2SO4. So this here, because it's a diprotic acid, requires 2 moles of base to neutralize it. So if we had 2 moles of base, there's only really 1 mole of acid present because 2 moles of base is required to neutralize that. So there's going to be interesting relationships like that. And then we're finally going to use stoichiometry to solve this. So it seems complicated, but it isn't too terribly bad. So how many moles of hydrochloric acid are needed to neutralize 0.5 moles of calcium hydroxide? This is an easy one to start. So HCl aqueous plus Ca bracket OH2 aqueous produces CaCl2 aqueous. There's our salt and some water. Now, the way I balance these equations is not so much balancing other ions. I balance the amount of hydroxide and hydrogen ions. I can see that calcium hydroxide produces 2 hydroxide ions, so I'd need 2 hydrochloric acids to balance them out. So if I have 2 H pluses and 2 OH minuses, that's going to make 2 waters. And then I balance everything else after. I can see 1 calcium on the reaction side, 1 calcium on the product side. So it's done after this. So my balancing numbers are there. So it asks how many moles of hydrochloric acid are needed to neutralize 0.5 moles of calcium hydroxide. So we don't have to deal with concentration in this question. We're simply just doing a mole to mole ratio. Hopefully something you remember from Physical Science 20. So we are given 0.50 mole of Ca bracket OH2. So we can see from our balanced chemical equation that 1 mole of CaOH2 neutralizes 2 moles of HCl. So when I multiply these, the moles of calcium hydroxide cross off, and I'm left with moles of HCl. So 0.5 times 2 means 1.0 moles of HCl was needed. Okay, so we don't have a device that measures moles. We have a device that measures volume, and we know the concentration. And we can take those 2 things and figure out moles. So you're not going to get an example like this, but it's important conceptually to understand that a neutralization reaction is based on balancing number of moles, not equal volumes or equal concentrations, but the number of moles. Okay. So here's our next example. A student titrates 21.4 milliliters of hydrochloric acid with an unknown concentration of that acid with 24 milliliters of a 0.0947 molar sodium hydroxide. What is the concentration of the known acid? The reason why we always know the concentration of sodium hydroxide is it's made by taking solid and dissolving it into water. So we can measure the amount of solid that we're using and how much water and get a very accurate concentration from that. Our lab, our scale here goes to the 3rd decimal place, so 1,000ths of a gram, which is pretty ridiculously small. So we can accurately measure exactly how strong our bases are. So let's start by writing our neutralization equation. So HCl aqueous reacts with sodium hydroxide aqueous to produce NaCl aqueous and H2O. This is our bread and butter neutralization equation. Both of these compounds are readily available in our lab and in most labs around the world, which means this is a pretty standard titration to be running. So what we know here is the concentration of the sodium hydroxide is 0.0947, and we use 24.0 milliliters. We don't know the concentration of the HCl, but we do know that we use 21.4 milliliters of that. So again, what I'm trying to do here is I'm trying to figure out the moles of the base, and then I'm going to use a mole ratio to go from moles of a base to moles of acid. And then I'm going to take the moles of the acid and divide by the volume of the acid, which is going to give me a molarity. Okay, so step 1, let's figure out the moles of base. So moles of base is equal to concentration times volume. Okay, so the concentration of this is 0.0947 times our volume of 24.0. Now, I've made a mistake here. Hopefully you recognize that, oh, wait, anytime we're working with molarity and volume, we have to be in liters. So I'm taking 24, dividing by 1,000, 0.24, or sorry, 0.024. There's another 0 on the end of that for sig figs. So both of these numbers have 3 non-zero numbers. So essentially I can use that in my answer. So 0.947 times 0.024 gives me 2.27 times 10 to the negative 3. So 2.27 times 10 to the negative 3 moles of NaOH. So we have to recognize that 1 mole of NaOH breaks down into 1 mole of hydroxide, right? So when we're saying 2.27 moles or times 10 to the negative 3 moles of NaOH, we don't really care about the Na. We care about the OH. So 2.27 times 10 to the negative 3 moles of NaOH were used. We're going to set up our mole ratio here. 1 mole of NaOH neutralizes 1 mole of HCl, which means we're going to get the same number. So 2.27 times 10 to the negative 3 moles. And then we should recognize that concentration of HCl would be equal to moles of HCl over the volume. All right, so moles per liter. So we're going to take our moles of HCl from up here. So 2.27 times 10 to the negative 3 moles, and divide by the volume. So converted to liters, 0.214, which is equal to 0.106 molarity. Okay. It looks like a lot going on here, but we really just have to organize it in our brain and get familiar with the steps of, okay, how much acid is required to neutralize this base, and then going through that process. In the lab, this would be a little bit different. It's a little bit more complex. We'll see one example with this shortly. But this is the backbone of this procedure, and that's not going to change. It's going to look similar to this for the most part. All right, with this one, we have more information given to us. So a student records the following data when titrating standardized solution of sodium hydroxide with an unknown concentration of hydrochloric acid. First, we're going to figure out the volume of sodium hydroxide used, determine the concentration of HCl, and finally determine the pH of the acid. Now, this fancy thing over here is called a burette. At the very top of it is 0. I'll write that in yellow so it's a little bit easier to see. At the very top of it is 0, and on the bottom, where it almost is empty, is 50. The reason why we fill this up. In science, anytime we need to take a measurement, a difference between two things, right, like change in volume, we always use volume final minus volume initial. So if we had 50 at the top when it's completely full and 0 on the bottom down here, let's say that we ran it all the way down to this mark here, okay? And this was, instead of 47, that would be 3. We'd start at 50, so, and end at 3. So 3 minus 50 gives us negative 47. See how that's a problem, right? Because it's always final minus initial. We want our final to be the high number and our initial to be the low number. So in this case, at the very top is 0 and on the bottom is 50. So it tells us here that the initial volume was 0.43. So that's right up to the top of the burette, okay? With these burettes, all of them can be read to 2 decimal places, and I'll show you why. Oh, let me redraw that a little bit better. There we go. All right, so the burettes will always look like this. Let's say that this is 12, and remember it counts up going down. The numbers get larger as we go down. That's a better way of saying it. Okay, so here's 12 and here's 13. And let's say that the water line was something like this. All right, so then the other side of the butyrate would be over here. Now it's got all these markers on it. Now, the way it works in science when we have an analog, right, a non-digital device, is we can read to 1/10 of the smallest division. So here, that mark right here is exactly 12, and this one is 13. So these 10 divisions in between, this would be obviously 12.1, this would be 12.2, let's try that a little bit better, 12.2, 12.3, so on and so forth. So this mark right here is 12.5. Now, the smallest division isn't 12 or 13. The smallest division is the ones in between. So I can clearly see that there's a difference. There's a marked difference between 12.4 and 12.5. So when I'm looking at this meniscus, does it look like it's right on the 12.5? No, it looks like it's in between the 12.4 and the 12.5. So 12.4 and 12.5, and it's not quite at the 12.5, but it's very close. If I was to take a green mark here, and I'm going to imagine this right in the middle of that, in the middle between 12.4 and 12.5 is 12.45. And I can see that it's past that mark. It's much closer to the 12.5. So when I'm squinting and using a piece of white paper in behind, and I read this really carefully, I could probably say that that number is 12.49. I say it's okay, it's really close. Okay, so that's how we get these numbers here, 16.31 or 0.43. This last digit here and this last digit here are estimated, but we still count them. Okay, so basically what happens here is we fill this up to close to around that 0 mark. We don't ever get right on 0.00 because that's nearly impossible. When you're dumping a bunch of liquid into it using a beaker, it's kind of got a top that goes out a little bit. So you dump it in kind of like a funnel. And when you're pouring it in, it's really hard to get to 0.00, but we don't care because we can measure accurately something that's close to 0, right? So in this case, we measure 0.43. So it starts at 0.43 at the very top here, and we let it run down. And then the student doing this titration, reads it again at 16.31. So when we're trying to figure out the volume here, so 16.31, we'd go VF minus VI. We've got 16.31 subtract 0.43, which means that it took 16.31 minus 0.43 gives us 15.88. So they used 15.88 milliliters, and that's our answer to question number 1. Okay, so these two numbers go together. There's our volume. It tells us the concentration of the base, and it tells us the volume of the acid that we used. Now, with all of that, we're going to be able to figure out the concentration of the HCl and eventually the pH of that using a calculation that we learned in topic number 5. Okay, so let's write our reaction here. We've got HCl and sodium hydroxide again. So HCl plus NaOH breaks down into or neutralizes to form NaCl and H2O. We want to figure out our concentration of acid. We don't know. Our concentration of base is 0.0503. Our volume here, and I'm going to convert this automatically to liters, 0.01588. 0.01588, and this is going to be 5 divided by 1,000, which is 0.05 over 1,000, should be 0.00. Yeah, 0050. Okay. Yeah. So now we're going to take our moles of base. So we want to figure out our moles of base first. So I'm going to go N. Yeah, we'll do it like this. NaOH. There we go. One more time. N in chemistry stands for the number of moles. So NaOH is equal to the concentration times the volume, which is going to be 0.0503 times 0.01588, which is going to give us a really small number. We get 7.98 times 10 to the negative 4. So 7.98 times 10 to the negative 4 moles of NaOH. Now this step here is the same thing. We're going to take our 7.98 times 10 to the negative 4 moles of NaOH, and we're going to say that 1 mole of NaOH reacts with 1 mole of HCl, which gives us 0.7.98 times 10 to the negative 4 moles HCl. Wow. You're saying, why do I need to multiply this by 1 over 1? It doesn't change it. No, it doesn't. For this reaction, it's very straightforward. It's a 1-to-1 ratio. That's not always going to be the case. So it's good practice just to get into that. So concentration of HCl would be equal to moles, which we've discovered, divided by the volume, which is going to be 7.98 times 10 to the negative 4 divided by 0.0050. Which gives us 0.159. Let's put an equal sign in there. So we get 0.1598 molarity if we keep that extra sig fig. All right, so we've done B now. Super easy with C. We should recognize that HCl, strong acid, breaks down into H plus and Cl minus. Therefore, concentration of HA, or in this case, we'll write it as just HCl. Concentration of HCl is equal to concentration of H plus. So therefore, the pH would be equal to negative log of 1598 molarity, which is going to give us a pH of 0.796. So before we move on, we should ask ourselves, does this seem reasonable? Does a strong acid that has a relatively high molarity, right? 0.1 molarity doesn't sound like very much to us, but we have to keep in mind that a neutral solution has 1.0 times 10 to the negative 7. So this is essentially about 1 billion or 100 million times stronger than that. So it's very, comparatively very strong. So does it make sense that the pH would be low? Yes. Okay, so we've got a reasonable answer here and we are done. This is the type of question that you'll see on assessments. All right, Chem 30, welcome back. We're gonna try 2 tougher titration questions now. The first one is something that you could be asked on an assessment, but the second one will not be part of this course. And we'll see why in just a second. But this one is more challenging because we don't have a simple monoprotic acid and hydroxide that only donates 1 hydroxide, or a compound that only donates 1 hydroxide. We've got calcium hydroxide, which donates 2, and we've got the acid, phosphoric acid, which is a triprotic acid. So let's start by writing our neutralization equation. So we've got CaOH2 aqueous reacting with H3PO4 aqueous, turning into Ca3 bracket PO4 2, that's our salt, and some water. Now, again, instead of balancing by ions here, I'd like to balance by hydroxides and H pluses. So we can see that phosphoric acid is triprotic, donating 3 H pluses, while calcium hydroxide donates 2 hydroxide. So I can't make either one of those equal, so I'm going to get them both to 6. And so when I do that, this becomes 3, this becomes 2. And then I can see that that balances those out. And I've gotten them both to 6, which means that I'm going to produce 6 water in the end. So now I've got 3 calcium on the reactant side, 3 on the product, 2 phosphates on the reactant, 2 phosphates on the product, and I've got the correct number of hydrogen and oxygen on the product side as well. All right, so I'm going to write my given information now sort of below this neutralization equation to make it a little bit easier. So what is the pH of calcium hydroxide if 200 milliliters is needed to completely neutralize 100 milliliters of 0.350 molarity H3PO4. So I don't know the concentration of that, but I know I'm using 0.200 liters. I've got 0.350 molarity phosphoric acid and 0.100 liters of that. So I can see that I know my moles of acid this time as opposed to my moles of base. So this process is going to be very similar. So instead of figuring out moles of base, I'm going to figure out moles of acid, which is equal to the concentration multiplied by the volume, which works out to being 0.350 times 0.100, which gives us 0.0350 moles. Right? Anytime we multiply by 0.1, it just moves that decimal over 1. So 0.0350 moles of H3PO4 was needed to neutralize this calcium hydroxide. So I'm going to use a mole ratio here. So because I've got moles of acid on the top, I want to cross that out. So I'm going to put 2 moles of H3PO4 is required to neutralize 3 moles of Ca bracket OH2. So I can see that I'm going to be essentially multiplying by 3 dividing by 2, or multiplying by 1.5. So 0.350 times 3 equals divided by 2 equals 0.0525 moles of CaOH2. Okay, it should be a better M. There we go. So 0.0525 moles of OH2. That gets us a little bit closer, but we're looking for the concentration. So the concentration of CaOH2 is equal to the moles divided by the volume. So in this case, 0.0525 divided by 0.200. Oops. 0.0525 divided by 0.2 equals 0.2625 molarity. Okay, so we're not done because it's asking for the pH. Now we should recognize that calcium hydroxide, when it breaks down to calcium 2 plus and 2 hydroxide ions. So if this concentration of the calcium hydroxide is 0.2625, we don't care about that calcium ion. We know that the hydroxide is going to be twice as large. So this is going to be multiplied by 2. So this works out to being 0.525. So that's the concentration of the hydroxide ion. So we have to be a little bit careful here that we don't fall into the trap of using a pH calculation right off the get-go. What we're going to do here, there's a couple ways we could approach this. We could, well, you know that concentration of the hydroxide ion, we could use the Kw value to convert that to an H plus and then do a pH calculation. But I prefer doing a pOH calculation. So pOH is equal to negative log of OH minus, which is going to give us negative log of 0.525. Works out to being 0.2798. 0.2798. And then we know pH is equal to 14 minus pOH, which gives us 13.72. And before we finish this question, again, we need to ask ourselves, does this seem reasonable? We should recognize that calcium hydroxide is one of the 8 strong bases that we recognize. So we expect it to have a high pH. Not only does it have a high pH because it's a strong base, but because it's a base that gives off 2 hydroxide ions, we expect that number to be even larger. So 13.72 is well within the ballpark of what we expect. All right, we got our last example here, which again will not be something that you would be expected to do in this course. It's just simply an extension of what we're learning, and it's a little bit more challenging. So a bad student at a North End school performs a janky neutralization. They add 45 milliliters of a 0.1 molar solution of sodium hydroxide to 50 milliliters of a 0.1 molar solution of acetic acid. What is the pH of the acetic acid after the addition of the sodium hydroxide? And what volume of sodium hydroxide is needed to fully neutralize this solution after the silly northerner has messed it up? Okay, so we're going to start by writing ourselves the neutralization reaction that occurs. So we got CH3COOH aqueous reacting with NaOH aqueous, producing CH3CO NaCH3COO aqueous and some water. Now, normally in a neutralization reaction, the amount of base and acid are equal. We're given both a volume and a concentration for both the acid and the base, hoping that they are equal. And we're going to see that that's not the case here in just a second. So we should recognize that moles of any substance is equal to the concentration multiplied by the volume. So I'm going to write the concentrations below here in red. I'm not going to show this calculation. I'm sure that you can do it. 45 milliliters divided by 1,000 is 0.045 multiplied by 0.1 would be 0.0045, and the amount of acetic acid is 0.0050. Okay, so these are both moles of these substances. We can see that it's a 1-to-1 ratio. 1 mole of this would neutralize 1 mole of that. So in turn, I can recognize that I'm going to have 0.0005, right? So I'll just write this out. There's going to be excess acid because there is more moles of it, more moles. So that the moles acid is equal to 0.005 subtract 0.0045, which works out to 0.0005 moles acid remaining. So now that we have that number, we are one step closer to solving the pH, or the pH of the solution, because we've got excess acid. It's going to undergo that acid equilibrium reaction that we would expect. But there's going to be a little caveat there. But let's write out that reaction. So we've got CH3COOH aqueous, and we ionizing into CH3CO minus and H2O. Sorry about that. H plus aqueous. There we go. So we've got, in this case, we can't use moles. So we have to be careful about this. Although we've got 5 moles remaining, the concentration now of the CH3COOH is 0.0005 moles divided by the new volume, because these solutions have been mixed. So it's 45 plus the 50 milliliters, which gives us 95, so that's 0.095. So this works out to being 0.005 divided by 0.095, 5.26 times 10 to the negative 3. So 5.26 times 10 to the negative 3 molarity. So let's try that one more time. We got 5.26 times 10 to the negative 3 big M here. So that's its initial change in equilibrium. But we should also recognize that this substance here is soluble in water. So whatever the concentration of this one is equal to concentration of the CH3COO minus ion. And that's what makes this a little bit more challenging. If we think sort of off to the side here, that this solution is these two substances, the CH3COOH and the CH3COO minus, are in water, recognize that CH3COO minus aqueous plus H2O will actually produce CH3COOH and OH minus. We should recognize that the acetate ion, CH3COO minus, functions as a Bronsted-Lowry base. It can accept a hydrogen. And by doing so, when it accepts a hydrogen from water, it produces hydroxide. So we have a little bit more of a complex reaction. Well, how much CH3COO minus are we? Well, we could normally just do a stoichiometry sort of question here and figure out based on the limiting reactant. But it's pretty obvious to see that all the sodium hydroxide is going to be used up. So the limiting reactant here is the sodium hydroxide. And because it's a 1-to-1 ratio, if there are 0.045 moles of the sodium hydroxide, it's going to create 0.045 moles of the acetate ion. So 0.0045 moles of CH3COOH minus exist. And for us to be able to put it into our ice chart, we have to figure out the concentration of that. So CH3COO minus moles divided by liters. In this case, it's going to be 0.0045 divided by 0.095, right? The total volume, which gives us 0.0045 divided by 0.095, 0.0474. 0.0474 is what it rounds to. So this number here is 0.0474, and we have no H plus. All the H plus gets neutralized by the available hydroxide. So there's none to start. So the neutralization happens, and then more of this acid will break down. We know that according to Hess's law, or Le Chatelier, it's going to be driven to the right to produce some hydrogen. If there's none there, it wants to reestablish that equilibrium, so it's going to decompose, which means that we're going to get this negative x here, this plus x here. So we get 5.26 times 10 to the negative 3, and then we get this 0.0474, and then we got, I'll rewrite this as 0 plus x, and then we get x here. Well, we're going to make that a double assumption here, that 5.26 times 10 to the negative 3 doesn't seem like a very large number, but it's minus x. I should have had that in there. It's essentially going to be 5.26 times 10 to the negative 3. This is going to be, even though it's plus x here, we're just going to assume it's 0.0474, and I'm running out of room, so I'm not going to show the 5.26 times 10 to the negative 3 subtract x is really approximately 5.26 times 10 to the negative 3. Same with the second one, but we get this. Okay, so now we can take these pieces of information and plug it into a Ka calculation. So we get Ka is equal to the concentration of CH3COO minus ion multiplied by the concentration of the H plus ion over concentration of the CH3COOH. So we get 1.8 times 10 to the negative 5 is equal to 0.0474 times x all over 5.26 times 10 to the negative 3, which works out to being 2.1. So 2.01 times 10 to the negative 6. So then our last step with this is a pH calculation. So pH is equal to negative log of H plus, which is equal to negative log of 2.01 times 10 to the negative 6, which is equal to 5.70. Okay. So after the sodium hydroxide has been added, this solution is still acidic, and that's what we would expect, right? They haven't added enough of that sodium hydroxide to fully neutralize the solution, so it remains acidic slightly, or it's much higher than it was, right? So 5.70 is actually pretty close to being neutral. It's not quite neutral. It's in that very weak acid range, but that's what we'd expect with this. So it asks, what is the volume of sodium hydroxide that needs to be added after the northerner has messed up to fully neutralize the solution? Well, we should recognize that there are 0.005, oh, just kidding, one more zero here, 0.0005 moles of acid left. So to fully neutralize it, we would need 0.0005 moles of base. Okay, and we know the concentration of the base is equal to 0.100 molar. So we can figure out the moles of base by going, or the volume of base required. So volume of base, if we think about that concentration triangle, I'm going to write it in black down here because I'm running out of room. This is our concentration. So moles on the top, concentration here, and volume. We're solving for volume. So volume is equal to moles divided by concentration. So we know the number of moles has to be equal. So we're going to write, well, we need 0.0005 moles. And we need, or the concentration is 0.100 molarity, which works out to be 0.0005 divided by 0.1 is going to just move the decimal over 1. And that's going to tell me in liters, which is not very useful. So I'm going to multiply by 1,000, and we can see that it actually works out to being 5.00 milliliters. Why? Because the solutions are the same strength. And despite one being a strong acid and one being, a weak acid and a strong base, it doesn't really matter. It's how much they protonate or how much hydrogen and hydroxide they give off. Because the weak acid gives off one hydrogen ion and the weak base gives off one hydroxide ion, it actually works out to being the same thing. Equal volumes of equal concentration would neutralize the solution. All right, again, this is not something that you'd be expected to do on any assessment. This is something that you can expect at post-secondary if you take chemistry there. But if this is all over your head, don't worry so much about it. Just recognize that there are more complex examples out there. All right, if you have any questions about anything else that we covered in this video, please let me know. Otherwise, have a great night, Chem 30.